The morning class, I had explained you about buffer capacity of a buffer solution. Now, in this afternoon class, I would like to introduce you to solubility product, to a term which is called solubility product. Now, before solubility product, try to understand what is solubility. This is a word which we have already seen in class 8 or maybe 9 or maybe 7 or 10. Now, the solubility of a substance is the amount of that substance that will dissolve in a given amount of a solvent. It may be considered to be an equilibrium. The equilibrium is between solid and ions in solution. Any ionic solid is 100% ionized in aqueous solution, and once it actually dissolves, so we get sodium chloride salt. If you put in aqueous solution, it becomes ions. Okay, so the ability the ability of a substance to dissolve in a particular solvent is considered to be solubility. Okay, now after this, what is solubility product? Now we know the solubility of a substance in water depends upon number of factors. Therefore, all substances are not equally soluble in water. Like salts like sodium chloride or potassium chloride, silver nitrate, etc., dissolve to a large extent in water. But on the other hand, there are several substances whose solubility in water is so small that they are termed as insoluble or sparingly soluble. Now, examples of sparingly soluble substances like silver chloride is there. Silver chloride is sparingly soluble, AgCl. Even barium sulfate over here. Barium sulfate is sparingly soluble. Lead chloride, silver bromide, zinc sulfide. Now, for this situation, when a sparingly soluble salt is dissolved in water, only a very small part of it dissolves and dissociates into ions. Remember that. And in a saturated solution of a salt, the ions formed remain in equilibrium with the undissolved salt. So, the equilibrium is dynamic in nature, and the rate of dissolution of ions from the solid is equal to the rate of precipitation of ions from the saturated solution. So, here we can talk about the equilibrium. There is an equilibrium whenever a sparingly soluble salt is dissolved in water. So, to explain that over here, try to understand this concept. Undissolved salt, undissolved salt, undissolved salt over here, it is in equilibrium with ions in equilibrium. Ions in equilibrium. Ions in equilibrium. Now here, let us take an example of a sparingly soluble salt like say silver chloride. If I take silver chloride and try to put the silver chloride salt, which is sparingly soluble in water, then it gives the following ions Ag plus aqueous and Cl minus aqueous. Okay. Now, if you apply the law of chemical equilibrium and the law of mass action to this equation, then we have an expression for the equilibrium constant, that is K, like this. Ag plus, concentration of Ag plus into concentration of Cl minus, divided by concentration of silver chloride. So this is the expression. Now, the undissolved salt present in the solid state, this is in the solid state, this one is in the solid state. So it is a constant. Its concentration is taken as constant. So if we write, if you take this K into concentration of AgCl, that is also a constant, and that is equal to the product of the concentration of the ions which are produced. Now this much, the product of the concentration of the undissolved salt and equilibrium constant K, this is called solubility product, KSP, and that is equal to Ag plus into Cl minus. Okay, so that is very important to understand over here. Okay, now this KSP means product of the equilibrium constant K and the concentration of the undissolved salt. And this Ag plus and Cl minus concentration, this is called, it is called ionic product. it is called ionic product. You have to remember this. Okay, that is very, very important over here. So on this basis, if you talk about mm, the solubility product, you can say it is equal to ionic product. So here you can say that the solubility product, the solubility product, the solubility product is equal to the ionic product, to the ionic product in a saturated solution, in a saturated solution. So that is important for us to understand. Okay, the solid product is equal to the ionic product in a saturated solution. So that's why remember KSP stands for soluble product, and the product of the concentration of the ions, like for this case Ag plus and Cl minus, these two are called what? Ionic product. Okay, now note that the solubility product of a sparingly soluble salt at a given temperature. If you talk about the solid product of given salt at a particular temperature, then it is the product of the concentration of the ions in the saturated solution, with each concentration term raised to the power equal to the stoichiometric coefficient of the corresponding ion. So this is the definition of solid product, which you can find from your textbook also. Now there are some expressions of solubility products for some sparingly soluble salts, which are written over here on your screen. So just try to follow them. Or if I take the sparingly soluble salt, say barium sulfate. So barium sulfate, it is a sparingly soluble salt. So at equilibrium, it is providing barium ions and sulfate ions in aqueous solution. So the soluble product for this sparingly soluble salt is equal to concentration, product of the concentration of barium ions and product of the concentration of sulfate ions. So this is for barium sulfate, the first sparingly soluble salt. The next one is zinc sulfide, which is another sparingly soluble salt. So in aqueous solution, it produces ions, zinc ion Zn plus 2 and sulfide ion S minus 2 aqueous. So the expression for the solid product is KSP is equal to product of the concentration of zinc ions Zn plus 2 and sulfide ions concentration. The next sparingly soluble salt is lead chloride, PbCl2, lead chloride. Okay, in aqueous solution it will provide Pb plus 2. Okay, it is provide Pb plus 2 plus Cl minus 1. Over here, the stoichiometric coefficient of Cl minus 1 is 2. So, what this, the expression for solid product becomes KSP is equal to concentration of Pb plus 2 into concentration of chloride Cl minus 1 raised to the power of 2. Okay, as per the definition. Okay, now moving to the other examples for this. This is I'll discuss this later on. The fourth example, okay, is Ag2Cr2O4. Okay, this is a dichromate ion, silver dichromate. Okay, now here this is also a sparingly soluble salt, so which in aqueous solution provides 2 silver ions plus chromate ion CrO4 minus 2 ion plus it's not plus only till here only. Now the solid product for this ionic reaction becomes concentration of Ag silver ions raised to the power of 2 into concentration of chromate ions. Okay, so that is the expression for the solid product for this reaction. Then the next example is calcium phosphate, is also a sparingly soluble salt, Ca3PO4 twice In aqueous solution, this is solid. Okay, it gives the following ions: 3 times calcium ion plus 2 times phosphate ion in aqueous solution, AQ. This is also in AQ. Okay, now the expression for the solid product becomes like this: KSP is equal to concentration of calcium ion raised to the power of 3 into concentration of phosphate ion raised to the power of. So this was some examples for the expression of solid product for some sparingly soluble salts which are written over here. Okay. Now I would like to define once more what is solubility product. The solubility product of a sparingly soluble salt at a given temperature. At a given temperature, it is the product of the concentration of ions. It is the product of the concentration of ions in the saturated solution. In the saturated solution. So you can see the definition over here. Okay, on page number 469 of the textbooks, which I am sharing on the screen. Okay, over here on the screen. The solid product of a sparingly soluble salt at a given temperature is the product of the concentration of ions in the saturated solution with each concentration term raised to the power equal to the stoichiometric coefficient of the corresponding ion. So that is what we have done over here in these examples. After this, there is one important relationship between solubility and solid product. Solubility is written as capital S and solid product is KSP. So a definite relationship exists between the solubility and solid product of a salt. This relationship is quite helpful in calculating the value of KSP of the substance. For a binary salt, if there is a salt which is binary, a salt of the type AB containing a cationic part and an anionic part, it is called binary salt, which is composed of two ions. It is called a binary salt. Suppose at a particular temperature, the solubility hello, can you hear me? Hello, can you hear me, boys?
Yes, sir.
Suppose at a particular temperature, the solubility of a given salt AB is small s moles per liter. That is the solubility unit for solubility. If the salt is assumed to undergo complete ionization into ions, S moles of AB will furnish another S moles of A plus and another S moles of B minus. Therefore, we have for this binary salt AB producing ions A plus and B minus. So KSP will be product of the concentration of A plus and B minus, that is S into S. That is coming to S square. So KSP for a binary salt is S square. Hence, for a binary salt, the solubility product is equal to the square of its solubility at a particular given temperature. That is for a binary salt. Now, looking at a ternary salt, a salt of the type AB2 or A2B capable of giving how many ions? 3 ions are called ternary salts. Suppose the solubility of a ternary salt AB2 is S moles per liter at a particular temperature. If you assume that the salt dissociates completely in solution, then S moles of AB2 will give S moles of A2 plus and 2S moles of B minus ion. Therefore, based on this, for a ternary salt, the working is over here. AB2 is giving A2 plus and 2B minus. So there are 3 ions, 1 ion of A2 plus and 2 ions of B minus. So KSP will be equal to concentration of A2 plus into concentration of B minus raised to the power of 2 according to the definition. So for a ternary salt, the solid product is equal to 2 to the 4s cube. It is equal to 4s cube. Therefore, we can say for a ternary salt, the solubility product, the solid product over here is 4 times the cube of the solubility of the salt at a given temperature. So 4 times the cube of the solubility. Okay. Now, table 7.4, have a look at table 7.4. The KSP values of various sparingly soluble salts are given at a temperature of 298 Kelvin. Just for your information, in the examination, if these are required, they will be given for calculation. So there is a numerical over here, direct formula based numerical. Example 7.31. The solubility of silver chloride at 298 Kelvin is given 1.3. 1.3 at the temperature into 10 power minus 5 moles per liter. Calculate the value of KSP. That means solubility means small s is given. So KSP for a binary salt is s square. So just write 1.3 10 power minus 5 to the power of 2. So the answer is here. That is the solid product. Similarly, example 7.32 also. The solubility of CaF2. This one is a ternary salt. So you have to remember 4s cube. In water at 298 Kelvin, it is given 1.7 into 10 power minus 3 grams per 100 centimeter cube. This you have to convert over here into liters. So 1.7 10 power minus 3 grams per 100 centimeter cube, it can be converted. That is equal to 1000 by 100, which is coming into liters. We are converting this per 100 cube into liters by this method over here. So it's multiplied into 1000 by 100. Okay, 100 is down already over here. On the top numerator 1000. So we get 1.7 per minus 2 grams per liter. So the solubility over here in moles per liter. So the molecular mass of calcium chloride is 78. So 1.7 per minus 2 or 78 will give the solubility in moles per liter. So because we know the molecular mass of calcium chloride is 78. So based on this, we write down the ionic equation over here. Okay, and then finally we have the value of this 2.18 per minus 4 moles per liter solubility. Okay, and then concentration of chloride ions, concentration of calcium ions. Okay, that is equal to concentration of calcium chloride. Okay, so it is a solid, and then write the formula for KSP, Ca plus 2 and F minus 2 raised to the power of 2, because it is producing 2 fluoride ions and 1 calcium ion. So put the values over here and get the answer for the KSP, solubility product. Okay, now where do we apply the concept of solvent product and common ion effect? So we apply, the first one is in calculation of solubility, which examples we have already seen. For binary salt, KSP is s square. For a ternary salt, KSP is 4s cube. Therefore, by having a knowledge of solubility product at a particular temperature, it is possible the solubility of given salt at a given temperature can be calculated. So examples are here. There is a salt, ternary salt, PbCl2. At 298 Kelvin, its solubility product is given 1.7 10 power minus 5. Okay, they are telling us to calculate the solubility. So they are telling us to find the value of S over here. So we know the value of KSP. So make S the subject of the formula. So it becomes 1.7 power minus 5 by 4 raised to the power of 1 by 3 cube root. Okay, so on simplification we get this answer. Molecular mass of PbCl2, we know it is 278. So whatever we get, it is in over here moles per liter. So converted into grams per liter. So divided by multiplied by 270 and get the answer in grams per liter. That is the solubility. Solubility you have to obtain always in grams per liter. Okay, then the next example under this is this one, example 7.34. The magnesium hydroxide, the solubility of magnesium hydroxide in pure water is given. So they are telling us to calculate its solubility in 0.02 m magnesium nitrate solution. So here solubility of magnesium hydroxide is given 9.5 grams per liter. Okay, get it converted into moles per liter, and magnesium hydroxide ionizes in this manner over here. Okay, so get the KSP by applying the formula, because concentration of hydroxyl ion is twice into concentration of this is given 1.6 per 10 power minus 4. Okay, we have calculated over here, and then in 0.02 m magnesium nitrate solution, the solubility of magnesium is assumed to be x moles per liter. So if this is x, this will be 2x depending upon the stoichiometric coefficient, and then on that basis it becomes 0.02. This will become twice into 0.02. Okay, therefore concentration of magnesium ions is x plus 0.02 and hydroxyl is 2x. So based on this, it is finally solved over here. KSP, product of the concentration of magnesium and hydroxyl ions, put the values, get the answer in terms of x. and it is a quadratic equation. Solve it. Okay, so x becomes over here this much raised to the power of half, because it is x square. You have to get the square root. So the answer is coming, solubility of magnesium hydroxide in the presence of 0.02 m is coming to 8.6 into 10 power minus 4 gram per liter. So this is one application, one use of solubility product and common ion effect. The other one is in predicting the precipitation of a salt, whether the salt will precipitate or not. So we know already that in a saturated solution, an equilibrium is existing between the undissolved salt and ion in solution. So at equilibrium, the soluble product is equal to the product of concentration of the ion, that is the ionic product. If somehow the ionic product becomes more, exceeds the soluble product, the equilibrium shifts towards left, that is ions combine together and get precipitated. So if the ionic product becomes higher, then then precipitation will happen, otherwise precipitation will not happen. So we can conclude that a salt gets precipitated only when the ionic product becomes greater than the solid product. So remember over here, for precipitation to occur, for precipitation to occur, for precipitation to occur, the ionic product, the ionic product must be greater than the soluble product. This you underline and put in your mind. So from this information we can find out whether a given salt will precipitate or not, whether it will precipitate or not accordingly. Okay. Now, after this, coming back to the textbook over here, thus the precipitation of a salt from a solution can be predicted by calculating the ionic product in the solution and comparing with whom? Soluble product. If ionic product is greater than the solid product, the salt will get precipitated. Otherwise, in the case ionic product is less than the solid product, the salt will not get precipitated. So there is a numerical based on this concept of solubility, whether a given salt will precipitate or not. So here example 7.35. It is given 25.0 centimeter cube of 0.050 m barium nitrate are mixed with 25.0 centimeter cube of 0.020 m sodium chloride. So there is a reaction between barium nitrate and sodium chloride to form barium chloride and sodium nitrate. Will any barium chloride get precipitated? That is what they ask. And they are given the KSP value of barium chloride. It is 1.7 10 power minus 6 atmospheric Kelvin. So first thing you have to do is get the moles of barium nitrate in 25 centimeter cube. Okay, so to get the number of moles, 0.050 divided by 1000 into 25. So that is 1.25 into 10 to the power minus 3. Number of moles of sodium chloride, again 0.020 divided by 1000. That is the formula we are applying for molarity. Okay, into 25 in 25 centimeter cube. We are getting 5.0 10 to the power minus 4. Now total volume of the solution mixing becomes 25 plus 25, that is 50. This means that 1.25 10 power minus 3 moles of barium nitrate and this 5 into 10 power minus moles of sodium chloride are now present in 50 centimeter cube of the entire solution. And then the concentration of barium nitrate in solution is given. It is 1.25. It is 1.25 over here. 1.25 10 to the power minus 3. The total thing is 50. Volume is 50. So if you divide this by 50 into 1000, you get in concentration in moles per liter. And the concentration of sodium chloride. So 5.0 10 power minus 4 by 50 into 1000, you get the concentration of sodium chloride. Hence, the concentration of barium ions is equal to concentration of barium nitrate in solution, which is 0.025. Okay. Therefore, ionic product of barium chloride can be calculated now. Okay, by applying this formula over here. Now we can see, compare the two values. Here, the ionic product of barium chloride is 2.5 10 to the power minus 6, and the KSP for barium chloride is 1.7 10 to the power minus 6. Which one is higher? Tell me. Is the ionic product higher or solid product is higher? Which one is higher? 2.5 is more or 1.7 is more? Yes? Is the ionic product more or the solid product is more? Here you will see that this 2.5 is more, which is the ionic product. So we can say that since the value of ionic product is greater than that of the solid product, the precipitation of barium chloride will occur. So that is what I have told you that time. Okay. So if the ionic product is higher than the solid product, precipitation occurs readily. So in a similar way, you practice example 7.36 also. Okay, 7.36. Okay. Now the concept of ionic product, solid product helps in the purification of common salt. You can purify sodium chloride. Then the concept of solid product is used for the purification of common salt. A saturated solution of impure common salt is prepared in a saturated solution like this. Okay, now HCl gas is passed through the saturated solution. This increases the concentration of Cl minus ions. Okay, due to dissociation of HCl, what happens? And the stage comes when the ionic product becomes higher than the value of Ksp for sodium chloride. Due to this, the pure sodium chloride gets precipitated and the impurities are separated in this manner. The most important application of solid product is in qualitative analysis of inorganic mixtures, in separating the cations in group 1, group 2, group 3, group 4, group 5. In the practical chemistry, you must have seen in the practical instruction that during the qualitative inorganic analysis, there is a chart where I have shown you how to separate the metallic ions or the basic radicals present in various groups. So the qualitative analysis of inorganic mixtures is based on the concept of solid product and involves the principle of selective precipitation. In this technique, the cations, commonly known as basic radicals, present in an inorganic mixture are precipitated selectively and tested one by one. So, in the systematic scheme of qualitative analysis, the cations, which are known as basic radicals, have been classified into groups on the basis of solubility products of their various salts. So, if you look at table 7.5, in group 1, the basic radicals which are precipitated are silver, mercury, silver and lead in the form of chlorides. In group 2, the basic radicals which are precipitated are sulfides in acidic medium of mercury, lead, bismuth, copper, cadmium, arsenic, antimony, tin 2 and tin 4. In group 3, the cations, basic radicals which are precipitated as hydroxides are aluminum, iron, chromium. Similarly, in group 4, nickel, cobalt, zinc, manganese in the form of sulfides in basic medium. Okay. In group 5, the basic radicals precipitate are carbonates, calcium carbonate or strontium or barium. And finally, in group 6, the basic radical is magnesium. It is precipitated as magnesium hydrogen phosphate. So here for the analysis of the basic radicals, the original solution of the given inorganic mixture is first treated with dilute hydrochloric acid when all the cations of group 1 get precipitated in the form of the chloride. This is what I have explained. Similarly, subsequently we can go to the other groups also and precipitate the others as and when required. So have a look at this. Hydrogen sulfide is a weak acid. It dissociates to give hydrogen and sulfide ions. So if we add a strong acid, because of common ion effect and buffer action, this strong acid is going to provide hydrogen ion, which is going to combine with the sulfide to give back hydrogen sulfide. So the dissociation of hydrogen sulfide is suppressed because of common ion effect. Thus, in acidic medium, only the sulfides of cations of group 2 get precipitated. Others will not get precipitated. So this concept helps in the precipitation of various basic radicals in different groups. Okay. So this has been discussed over here. You can go through this carefully on your own. Okay. That is for group 3 is also given. Group 4 is also given. Group 4 we add ammonium carbonate and ammonium chloride, okay, to suppress the decomposition of ammonium carbonate because of common ion effect. Okay. So now after this, the next thing that we'll discuss in this chapter will be not this is not in the syllabus, acid base indicators, which is not there in the syllabus. This we will not discuss at all. The next thing which is left for all of us in this chapter, it is hydrolysis of salts. Now this hydrolysis of salts, which I have already told you in one of the previous classes, whenever a salt is added, whenever a salt is put in water, it undergoes hydrolysis. It undergoes what? It undergoes hydrolysis. Now this, when I explained in the previous class with regard to hydrolysis, I have told you that if I take sodium chloride salt and put the sodium chloride salt in water, it is going to combine with water, the ionization, to give sodium hydroxide and hydrochloric acid. Now this formation of sodium hydroxide and hydrochloric acid is because of hydrolysis. Sodium hydroxide is a strong, it is a strong alkali. It is a strong alkali, and hydrochloric acid is a, it is a strong acid. So this is called hydrolysis. Now coming back to the previous explanation on the textbook, hydrolysis of salts, we have seen that water is a weak electrolyte and dissociates to a very small extent into hydrogen ions, that is hydronium ions and hydroxyl ions. In pure water, there exists an equilibrium between the undissociated molecules and ions, and the concentration of H plus and OH minus ions are equal. That is how we get the ionic product. Okay, that means pure water is neutral. So ionic product is Kw. Ionic product is Kw. It is the product of the concentration of hydrogen and hydroxyl ions. But if we talk about salts, which are strong electrolytes and dissociate almost completely into the constituent ions in solution, so when a salt is dissolved in water, the cations or anions of the salt may interact with the H plus and OH minus ions of the water, and they will disturb their equilibrium. Consequently, the solution may turn acidic or alkaline. This phenomenon, it is known as salt hydrolysis. Okay, so whenever we add salt in water, the H plus ion and the OH minus ion from water, they interact with the cations and anions of the salt to make the solution either turn acidic or alkaline or maybe neutral. So this phenomenon is known as salt hydrolysis. So definition is given over here. The phenomenon involving the interaction of cations or anions or both of a salt with the H plus or OH minus ions of water, leading to the formation of an acidic or alkaline or sometimes even neutral solution, is called salt hydrolysis. Okay, so this is the meaning of salt hydrolysis. So this brief discussion of the hydrolysis of different types of salts I will do in the next class tomorrow. So because I will not be able to complete it, so I'll stop my class over here only. Just hang on over there for some time because I will record your attendance. I will record your attendance very soon. Okay. But before that, I need to make sure that the screen is not being shared. Okay. So uh, your attendance, it's downloaded. Okay. Now, thank you so much. Have a nice day. Let us meet tomorrow.